What? Okay, I guess I'm recording on the cloud again. Anyway, to start with, I just handed back assignment 5, and there was one problem that a lot of people kind of messed up on that, which was number 55. And there's a common confusion when you're doing these things. So these are the ones where you got to find the moment of a force about an axis, right? So you got to find the moment of F, which is this force, about the AC axis there. And the way you do that is you find, well, in this case, the force is given to us as a Cartesian vector. And you got to find the moment of, the moment is the unit vector in the axis that you're trying to find the moment about, dotted with the cross product of some position vector like RBC cross F. And yeah, I think a lot of people got that okay. But then when they set up the matrix to do that, a lot of people got confused. So the unit vector is truly 0.86 plus 6, or 0.85 plus 0.6j, but you don't put I, j, k across that, right? You just do the determinant of the unit vector, which is on the first row, the position vector, which is on the second row, and the force vector, which is on the third row. That gives you a scalar, not a vector. Okay, like about 3 or 4 people were doing that. That scalar is the magnitude. There was also a sign error in the position vector. It's -2 in the k direction. So it's not 19.2 I plus or minus 4.8 j. It's 19.2 minus 4.8, which is 14.4. And that gives you the magnitude of the moment about the AC axis. To find the vector of the moment about the AC axis, you have to multiply again by the unit vector UAC. And that's when you get the 15.5 minus 8.6. 15.5 I minus 8.6 j, something like that is the answer. So check that out if you're confused. Any questions on homework 6, the last homework that's going to be on the exam next week? Have any issues with that? Good, then the plan for this week is we're going to look at, start moving into chapter 5, and I will be giving you a practice test towards the end of the week for you to practice test 2. Practice, we'll go over that on Monday. So we'll have 2 problem sessions again this week, I think, and then if there's time, if you have any questions, we can go over any issues you might be having with chapter 3 through 6, the stuff that's going to be on the test. So we've done equilibrium problems already from chapter 3, and those were situations where we had concurrent force systems. That's where all the forces were pointing to one point or leaving away, pointing away from a point. Today we're going to be looking at a more general class of problems called rigid body problems. They're not just points; they're actually structures. We're getting into more real problems. And you can do these in 2 and 3 dimensions. We'll be kind of spending a couple weeks on this chapter. But all the stuff we've been building up, all the stuff in chapter 4 was kind of just practicing techniques we're going to be using in chapter 5. So there's a conceptual part about Newton's stuff. You know, if a support presents a translation of a body, then the support must be exerting what kind of thing on the body? A force, right? Yep. Forces are what cause translations. Translation is just a sliding in one direction. Internal forces are what shown on the free body diagram. The whole body. Never. Yeah. Never. What is an internal force? Forces within the system, good, yeah, or within the materials that make up the components of the system, right? Those are also internal forces. So if you're more the simplest thing, if you're looking at a beam that's got two supports here and a load on it, the external forces are the forces of the support, and internal forces would be like if you broke that thing open and you tried to look at what the atoms themselves are doing across all of the boundaries in that material of the beam. Those are internal to the beam, internal to the system. They don't count, they don't apply, we don't pay attention to those when we're doing a free body diagram. Later on, we're going to be looking at those internal forces, and we're going to really kind of conceptually cut the thing, and then we can label the external forces at the cut, where we cut the material. So we can determine what those internal forces are, but you always have to do it when they appear as external to the body. So we're always going to look at just the external forces. So here's an application: platform suspended, from a tower. We might want to know what are the forces acting at the joints and in the cables. And typically what happens in real life, you're dealing with some real structure, and we then go through and idealize it. So we maybe look at it just in 2 dimensions if there's a lot of symmetry there. There's nothing different in the 3rd dimension. And then we turn it into a free body diagram, right? So this is the free body diagram. The free body diagram has everything you need to know to write the equations of equilibrium. Okay, notice all the angles that we need are there. Even if the angle's somewhere else, you got to put it on the free body diagram to make it correct. Okay, so that's showing you the forces, at the pin, the force from the cable, the force of the weight, all the forces acting on it. So which diagram is the idealized model? No, that's the free body diagram. What? Yeah, the middle one is the idealized model, right? The photograph is the more realistic one. The middle one is the idealized model. And typically what you're going to get in the homework and problems are going to be the idealized model. They're not going to give you a photograph to solve. They have to put dimensions on it and stuff like that. But the idealized model doesn't have any forces labeled. So you have to look at that idealized model and figure out where the forces are going to be in general. That's what you're going to do. And it's an act of understanding the concepts, the physics that's going on there to be able to do that, right? So all that physics 3A stuff comes in handy when you do that. Again, here we have a real situation, an idealized model where those roof joists are laying on that beam, and we're asked to find the support reactions at A and B. And this also is the idealized model. Are there forces missing on this beam? Yeah, what forces are missing? What forces are not shown on that diagram that are acting on the beam? Normal forces? Where are those normal forces applied? A and B. There are support forces, and we're going to call these reactions because if the beam didn't have any weight, in an idealized sense, there wouldn't be any need for these reaction forces. Like if gravity wasn't acting, you wouldn't have any forces needing to push it up. It would just be floating in space. When a body is in equilibrium, it's either moving at a constant velocity or it's not moving at all. And we're looking at these class of problems, which I call rigid body equilibrium problems. And equilibrium is that notion of stability, of constant constant velocity, mostly 0 in this case. In statics, it's always 0. Rigid means that it's not deforming under a load. It's not going to bend at all. And by saying it's a body, that means the forces are not necessarily concurrent. Concurrent forces were what we did in chapter 3. In our new situation, our body can be some amorphous blob. Forces could be acting at it. They look like they might be concurrent, but they're not. And you can also have moments acting on the body as well. And these M1 and M2 are couple moments, but remember, you can always replace couple moments with what? Two forces equal and opposite, right? And what direction would those forces be in? Or what plane would they be in? Well, they'd be in a plane normal to the moment vector, right? So you could have, you know, a force like this and a force like that. You know, this could be F2A, F2B, separated by some distance d. When you multiply F2A times d, you get M2, the magnitude, right, in that direction. Were there actually handouts on the top of that cabinet? Oh, you found one. Oh, good. They thoughtful classmates. Yeah. So anytime you see a moment, realize it's just two forces in opposition separated by some distance. There's no mystery to that. But in order for this body, this potato-shaped thing, to be in equilibrium, the sum of all the forces has to be equal to 0, and the sum of all the moments about any point in that body, they have to also be 0. Okay, that gives us up to 6 equations of equilibrium, because there's 3 dimensions in each of those equations. So the problems get more complex. They can be anyway, or they can be set up so that we only have a smaller number of equations. But the equations in general are going to be this vector equation. Some of the forces equal 0. That means some of the x components, the y, and the z components separately, individually has to equal 0. Same with moments. The sum of all of the moments along the x, y, and z axes has to be 0 for that thing to be in equilibrium. We're going to be looking later in chapter 5 at problems that actually have unknowns. Those are more challenging to solve, but we're going to be focusing earlier on with just problems that are in 2 dimensions, which will have like 2 forces, just like 2 forces and a couple moments that we're going to be looking at. So in 2 dimensions, we can throw out some of those equations. Typically, it's going to be something like this: 3 equations, 3 unknowns. In 2 dimensions, when you only have 2 dimensions, you can only have 3 equations and 3 unknowns. The equations that in 2D that you can use, you can also do 2 moment equations. A moment about 2 different points is also fine, and one sum of forces, and those can be arranged differently. You can also do 3 moments equations. Typically, it's either going to be, you know, 1 force and 2 moments, or 2 forces and 1 moment when we solve these things. An example problem. And in this diagram, this is an idealized diagram. It's not a photograph. It is a 3-dimensional problem. And you've got a beam with a planter on it and a couple of cables holding that thing up. And when we want to solve this, the first thing we're going to do is we're going to have to write that free body diagram. And the way the free body diagram works is we have to first isolate the body from its surroundings. And what is the important body in this problem? What's the thing that all the forces Well, you might think of point A as being an interesting point. And in fact, point A is a concurrent force system, right? There's 4 forces acting on it. If we're given the weight of the pot, could we determine all the forces acting at A? Yeah, there'd only be 3 unknowns, right? 2 forces on the cable and 1 force on the pole pushing out. But the complete system can be kind of described more fully by this beam OA. And that's not a concurrent system because there's extra forces acting at O there that have to be considered as well. So the body we're going to isolate in this case is the beam. And we're going to show the forces including gravity, any externally applied forces. Usually those might be given, like the weight of the pot would have to be given. And then the reaction forces, which are the forces at the supports that are keeping that thing from falling. And then we want to identify the forces with like variables or labels so we can actually then create equations involving them. So if we've got this flower pot problem, the free body diagram for that would be a simple beam. We're going to just isolate that beam from the whole problem. It's free. We're ripping that thing out from all of its supports. And we're in place of those supports, we're going to include the forces that those supports are acting on. So one force, obvious force, is going to be the weight of the planter, right? So here at A, we're going to have the weight, so P, the weight of the planter. And this you could do as a Cartesian force vector with just a single component J. You might also be considering the weight of the beam. We're calling this W sub S. I don't know why it's an S, but that's a beam, and the beam might have its own weight, in which case there's going to be a minimal set of reaction forces no matter what, even if there's no planter on there. You can also see that you're going to have a tension here, 2 tension forces, T, AC, and T, AB. Those forces are acting at the end, and they're pulling the pole towards the wall and up a little bit as well. And then at O, there's going to be some other forces. What do you have there? What does that look like at O? And you're going to see some really interesting, structures and interesting supports in this chapter. What does that thing look like at O? No, I mean, what is this thing there? Kind of like a pin, like a door stopper. Like a ball in socket. Where did that come from? The unconscious, right? It's a ball in socket. It's a like we have one in our body, right? Our hip joint is like a ball in socket, right? And the ball, which is the circular part on that beam, is held captive by the socket, but it's free to rotate, right? Free to rotate this way, that way. We have amazing joints in our body that allow us to move in a lot of different directions. Hip joint is one of those, really essential for walking. A ball in socket. And does that socket keep it, it doesn't keep it from spinning, right? So is that providing any moment on that beam? Any reaction moments? Could it provide any reaction moments on the beam, or is it just going to let it move? Right, it's just going to be free to move. So the nice thing about a ball and socket is there's a restricted number of forces that it will apply. It's only going to keep it from translating, right? The socket keeps it positioned in one X, Y, Z place. And to do that, if the beam wants to go up there, the socket's going to push down on it, right? That's going to be a reaction force. If the beam wants to go down, the socket's going to be pushing it up. If the beam wants to go out, it's going to be pulling it back to a point, and left and right as well. So there are 3 unknown forces, and you have to sort of reason your way. And there is a cheat sheet or a table of all the reactions that these joints can actually apply on a body. And but we can see that we're probably going to have an FOY that's going to be pushing out to counter the tension of the cables pushing it in. We might have an FOZ here pulling it up, most likely, and maybe if there's an imbalance on the cables, an FOX. And those are scalar magnitudes because you can draw that all as one single reaction force that's a Cartesian vector, or you can think about those components going up and to the right and into the or out of the page. So if you knew the weight of the beam and the weight of the planar, there would be 5 unknown forces. You have enough equations to solve it. Okay, and that's a general idea. But the question of these support reactions is a little mysterious the first time you see it. There's several types of reactions that we're going to have. A typical one in 2 dimensions is going to be a simple pin. A pin in 2 dimensions is going to, well, if you look at it on the side, it looks like that. If you look at it, you know, along the beam, it looks like that. It's not going to prevent any rotation in the XY plane of that beam. And there's sort of a conceptual, mental, visual reasoning you can do. Imagine you're trying to yank on that thing with your hand. Which type of motion that pin is going to restrict? It's not going to keep you from. It's not going to keep you from rotating it, right? But it is going to keep you from pulling it this way, up or down, or in or out. It's going to keep you from doing that. So there's going to be reactions there that are going to be force reactions. And so we can replace those, we can replace that whole pin with the forces that it exhibits, the forces that it exerts on the body of interest, right? So we get rid of that whole pin and replace it with the corresponding reaction forces that it's exerting on the body. This is our free body diagram. There are no pins on the free body diagram, just the forces that the pins exert. Okay, pretty cool. Other examples, you might find a roller. Here's a roller. There's also things called rockers, or a smooth surface, which would be considered like frictionless. Those things just have a single force normal to the surface. It's a normal force, so it's just pushing out at whatever angle it needs to be perpendicular to that surface. A little geometry quiz. If this angle is theta, what is this angle phi here from the horizontal for that normal force to be at? Should be 90 minus theta, right? Because if it's truly normal, this has to be a right angle, and it's even drawn here as that right angle symbol, right? So that's a 90-degree angle. The angles have to add up to 180, so therefore phi has to be 90 minus theta. So that's good to know. A smooth pin or a rough surface has an Fx and an Fy, or a force and an angle. You might also find a fixed support. That's where you just bury that whole support into a wall or something, right? And a fixed support, because the thing is embedded in here, it's not only going to offer an Fx and Fy, but also a couple moment. And the couple moment comes from, it's kind of interesting when you sort of think about what's happening. If you stuck a, like a plank or something in a slot, that plank would start to droop, and it would rest on like the rim here, which would be providing a force pushing back. And also internally here, it would also rest on the ceiling of that slot. And these two forces would provide the couple moment separated by some distance. And so this M would be the F times D. of these two forces acting to hold that thing up, right? That's how you get that moment in there. There is a more complete table in the text, and I do believe if you don't have it handy, I think I have these two links here in today's lecture on Canvas. These are photos or scans of the book showing you all the different types of reactions you can have. So there's a table there. You could probably just Google a table of support, support for rigid bodies in 2D, and you'll see that there. There's again a smooth surface, you're just normal to that surface. A roller pin confined to a smooth slot. Again, that's just going to give you a normal force. You might have, a collar on a rod. That's going to also just provide a normal force. So these are types of things you can get. Also, there's your smooth pin, fixed on a smooth rod. Again, it's going to be, well, you can have a normal force, but also because of that collar, you can have a moment provided, a reaction moment provided. It's going to keep it from rotating in the XY plane. And then there's your fixed support. Here are some real supports. This is a rocker support for a bridge girder. Allows a little bit of horizontal movement, so the bridge is free to expand and contract. There's a pin, a cable attachment. There's a great truss bridge on our campus over the ravine there, and one of these days we can go out and take a look. I think when we do chapter 6, we'll maybe take a look at there. It's kind of fun to see. There is actually, it's not a rocker, but there is a joint that allows the bridge to expand and contract. So we model it as a roller in a lot of our statics problems, but in fact, it's kind of like there's like a screw. It's a slotted screw thing, and it just sort of the screw will sort of just slide along, but it'll sort of anchor it in there, but allow it to expand as needed. And you have to do that for so the material doesn't get stressed by thermal fluctuations. Again, there's some other real supports. We spend a lot of time, typically you're given the idealized support, so you don't have to like think, well, what is this thing actually doing? Yeah, that's how it works. Very good technical stuff. And so another example. Well, actually, now we're just going to do a few examples, right? In this problem, you have a beam resting across, an opening in a building, and you could imagine this beam is probably anchored on one side. Maybe it looks like there's a little bolt there at A sticking up there. I can't really see, but that anchor could be modeled as a pin. It's not really a pin in the sense of what the diagram below looks like. And then there'll be like a roller. Again, that just sort of means that that beam could expand and contract due to thermal fluctuations, because it's going to do that. And then the joists that are resting on it are replaced by the simple forces. Oh, yeah, so we remove those supports and replace them with the reaction forces like FAY and FAX. There could be an FAX, although there's not really often a need in some problems to have that. Maybe the weight of the beam will be given to us, so we would add that in the middle. And then we would also have just a vertical force Y there. The reason we have an FAX is why? Why is there an FAX on the left but not on the right? Yeah, you could bring the wall into it, but in the idealized picture, it's this pin here, right? And then that pin is going to resist translation either into the wall or out of the wall, right? The wall itself wouldn't prevent it from going this way, but you're right. It could prevent it from going into the wall, but there would probably be some bolts stuck there at A to kind of keep that thing pinned on one side, and then it's allowed to shift on the other side. Okay, fine. Again, we have this platform which we looked at earlier. this idealized drawing. Now we got to draw the free body diagram, right? And the free body diagram is of that platform is we're just going to separate that platform from its surroundings. And at the pin, we would draw two forces there. One which would be pushing out, FAX, and one that would be pushing up. At B, we would have this tension force. To be complete, we would have to draw that 70-degree angle. We should also label the relevant dimensions, like this distance here is 1 meter. There's also a center of gravity on that guy, so we're going to have to put the weight from gravity. And then we would definitely want to put these dimensions here. Oops, 0.8. Having done that, you're now ready to write all the equations of equilibrium. So you can write, all angles and dimensions. That's what the free body diagram has. All angles, all dimensions, all reaction forces, and external forces applied to that body. Okay, if that sort of makes sense, let's try this, this concept quiz here. The beam and a cable has a frictionless pulley at D, supports an 80-kilogram load at C. If we're diagramming just the beam, how many unknowns are there? So we're given frictionless pulley at D. We're given 80-kilogram load at C. If we're going to diagram that beam, how many unknowns are there? So this is 80 times G, right? Sorry? 2? The answer is 2, in other words, 3 forces and 1 couple moment, or is the answer, yeah, they're saying 3 forces and 1 couple moment. You may have a different answer. Joel, what do you think? 2 forces and 1 couple moment? Okay. Spot check. Ezekiel, what do you think? 3 forces. 3 different answers. Let's see. Alex? Thinking 1, another vote for 1. Okay. Sabine? Yeah, you look like you want to say something. You want to change your answer to 1. Okay. Anybody else? Jonathan, what do you think? 1. 1. Okay. Okay, so where would we draw the 2 forces? The tension would be one force at E, right? And B, so is there TE and a TB? They're the same tension, because a frictionless pulley, they're going to have the same tension on each side of a frictionless pulley, right? So, okay. So we have those two. Well, actually, so that's just one. So where is the second force? Two forces in one couple moment. Connie? Yes, reactions are forces too. Two reactions at point A, yes. They would be like X and Y, right? You can do FAX and FAY. Eventually, we kind of just go to like AX and AY. Those are forces, right? Keeping that beam stationary. And then where would the couple moment be? Sorry? Sorry, Dylan? You see a what? You see the weight of the beam. Yeah, there could be a weight of the beam, but they're not giving it, they only told us it has an 80 kilogram load. You can assume that the beam is a lot lighter than 80 kilograms. In that case, it's sort of insignificant. That's kind of how a lot of these problems are formulated. So, I mean, unless they gave you the weight of the beam, you don't have to worry about the weight of the beam. So is there anything else we need to add to this free body diagram? Victor? The 4, 3, 5, good. Yeah, that's good. We would want to know the angles, so 3, 4, 5. Also, like the dimensions, that would be good. Yeah, now we could do moment equations, because in order to solve for the forces, we would actually have to do at least one moment equation. But there aren't any couple moments being applied to that structure by the supports or any external couple moments. So the answer is what? 3, right? It's just 3 unknown forces. We got to find AX, we got to find AY, and we got to find T. So that's a, until you do a few of these, it takes a while. These support reactions are a little confusing until you do a few. But then once you kind of visualize it, it's not too big of a deal. So here's some kind of a brake pedal. Again, these are I don't know why you wouldn't really anchor this. This looks like your anchor. That doesn't make any sense. But you can just imagine that somewhere in here there's a brake that's pushing against the hub of the wheel or something. So they're just modeling that. Again, this is idealized, right? You wouldn't really necessarily, set up a structure like this because this looks like it can't move. Why would you even need the spring, right? But it's modeling the fact that, where these forces are actually coming from. Right? So we can draw whatever that thing is, the bracket doohickey, and label all the forces acting on it. So what forces are acting on this guy? At B, somewhere in the middle here. At A. Right, well, we've got this external force acting on it. But what else is acting on that thing? Pardon me? The pin's going to have what? Sorry? A vertical and a horizontal component. And then we're going to have what else? tension force, right? The spring, Fs, and another tension force here, FB or TB, whatever. Now, all these horizontal forces are going in the same direction, so they can't all be positive. One of those is going to have to be pointing in the other direction. And you don't have to worry about the sign of these things. You're going to find when you do the calculations, one of them will be negative, and that's fine. When I grade these, yeah, you might, if you're, once you get good at doing this a few times, you might be able to intuit that AX is pointing in the opposite direction. It's probably pointing, like, right, if you're pressing on that pedal, and you're creating a tension on that spring and a tension on this cable, those tension cables are going to be resisting, because you're trying to make this thing rotate this way. The tension cables have to keep that from happening by providing a counter moment about A. And therefore, in order to keep this pin, this whole thing from moving to the right, we have to have a force at that pin pushing it to the left. So AX would be negative. But if you just draw it like that, that's fine. Just make, I'll just look to make sure your AX is negative. If you end up getting an answer that says AX is positive, that would be considered a sign error, because according to your diagram, AX should be negative. Does that make sense? So I'm just sort of looking for consistency when I grade these things. Your signs, should be consistent with the reality of which direction the force is actually going. Another thing that's going to come up from time to time is something called a two-force member. And a two-force member is a member that has forces acting on it at only 2 points. So like this cable here would be considered a two-force member. If it's full, if this bracket thing is feeling a pull at FB to the right, what is this cable feeling at point B? Yeah, that cable is feeling the exact same force, only because that cable is feeling like it's trying to be stretched out, right? When that foot is pressing on the pedal, that foot is pressing on the pedal, we're putting tension on that spring on that cable. That cable wants to be stretched out. So that cable feels that same force that we drew as FB in the bracket diagram. It's feeling that same force, but going in the opposite direction. And when you have a two-force member, how many unknowns are acting on this thing? How many unknown forces are acting on that thing? Sorry? 0? Well, before you solve for FB some other way, there's at least one unknown on there, right? Is there another unknown force on that thing? Yeah, a two-force member, it only has one unknown, because the magnitude of FB, we should probably call it FB1 and FB2. The magnitude of FB1 has to equal the magnitude of FB2. Why? If it's in equilibrium, right? They have to be the same. They have to add up to 0. Also, the direction, actually, why don't we call this point D here, and let's just call this FB equals FG. Sorry. So if we label this thing as D there, FB and FD have to be the same. So when you solve for one, you solve for the other. Also, the direction has to be what? They have to be equal and opposite. And also, it has to be oriented along the line what? Yeah. The direction of FB would be a unit vector going from D to B. How do I know that? Why can't FB be going in a different direction? I mean, what if I thought maybe FB could be going this way and FD could be going this way? Could that be possible and be in equilibrium? Why not? Because then you have a moment, right? You've now got a couple moment. So the thing's not going to be in equilibrium, right? So that's not allowed. The only way that this two force member could be in equilibrium is if the forces are acting along the line of the points where the two forces are acting, right? So there's really only one unknown. You know the direction of the force, you just don't know the magnitude of that force. Well, there's a couple other examples. Again, you've got this cherry picker thing, and suppose you are looking at that beam here, and the platform has some force P acting on it. And they've labeled G, which is the center of gravity, so presumably they're going to tell you how much that thing, the mass of that cherry picker. And then there's this stuff going on here at C, and at A, and at B. So what's happening? Well, actually, B is not even on this beam. So let's think about what's happening at A. What kind of reactions would we be seeing at A? What kind of support do we have at A? You've got a pin there, right? And that pin means you're going to have an AX and an AY. But what's going on at C? C is also a pin too. Is there a CX and a CY there? Well, you might think so. But the thing that's connecting C to B, which is another pin, is this rod here. Now this rod has forces acting only at two places. So that's a two-force member. If it's in equilibrium, we know the direction of that force that thing must be experiencing, right? It must be experiencing a compressive force going this way and this way, right? Can you imagine? It's got to be feeling a compression force, right? It's keeping that thing from collapsing. And the direction has to be oriented along the line from C to B. So you can call this force FC times, if you care for it, UCB, right? And this is F, it's the same magnitude, FC times UEC, just going in the opposite direction. We know the direction, right? So we know the direction of FC that member must be experiencing. So it's pushing back an opposite force in the same direction at C, right? So it's got also a single unknown here. Pushing back. So this is, we know the direction. So only FC is unknown. Theta is could come from the geometry of, the orientation of BC. So theta is not unknown. So that's a two-force member, and that means we only have three unknowns on this force. Three unknowns is the maximum number of unknowns you can have in a 2D problem, right? So that's how we can actually solve this. Finally, I'm going a little bit late. There is, sometimes we get these cylinders, and sometimes you get a system of forces. And why don't we just do this one tomorrow? We're already kind of late. we'll pick up this tomorrow, and then we'll continue with the next lecture. The next lecture, we're going to actually solve these. We'll actually find the forces tomorrow in these types of problems. Today was just kind of working on the free body diagram, the concept stuff. The reason we had to take 3A before this class, kind of for these situations here. No, I think it's one of them. Yeah. Oh, that's good. It's good. Thanks. Yep, there. Awesome.